Last time we took the bins out of a network and watched 105 numbers collapse into one straight line, 88%. Then we put a single function back in the middle, changed nothing else at all, and the same network went to 100%. And underneath it, the whole time, there has been this 0.0018. I have put that number on screen in all three of these videos. I have called it the loss. I have told you that smaller is better. I have never once told you where it comes from. So here is the whole problem in one question. The network says 0.7. The right answer is 1. How wrong is that? You probably said 0.3. That is the obvious answer. It is a perfectly reasonable answer, and it is not the answer that almost any real network uses. Because wrongness is not a fact about the data. There is no quantity of wrong sitting in there waiting to be measured. It is a rule that somebody writes down. And the rule you pick does not merely score the network. It decides what the network becomes. So let us take two rules and watch them disagree. One prediction. The true answer is 1. And I am going to slide that prediction from 0 all the way up to 1 and score it both ways as it moves. The first rule is the obvious one. Take the gap and square it. Means squared error, and it is what you would invent in about 4 seconds. At 0.7, the gap is 3/10, and squared that is 0.09. At a half, a quarter. At 0.1, 0.81. At 1 in 100, 0.98. The second rule looks like somebody invented it to be awkward. Take the probability the network gave to the correct answer, and take the negative logarithm of it. Cross-entropy. At 0.7, 0.36. At a half, 0.69. At 0.1, 2.3. At 1 in 100, 4.6. Both rules are 0 when the prediction is perfect. Both grow as it gets worse. So far they agree about everything that matters. Now watch the far end, where the network is badly wrong. This is where they come apart. Squared error has a ceiling. The very worst thing it can ever say about the worst prediction that exists is 1. Cross-entropy has no ceiling at all. At 1 in 1,000 it says 6.9. At 1 in 1,000,000, 13.8. At 1 in 1,000,000,000, 20.7, and it keeps climbing forever. And that logarithm is not decoration. Take it in base 2, and it is measuring something specific. Surprise, in bits. A prediction of a half is exactly 1 bit of surprise. A prediction of 1 in 100 is 6.64 bits. So one rule is asking how far off you were. The other is asking how astonished it ought to be that you were wrong at all. Which sounds like philosophy, right up until you look at what each one actually does to the training. And that turns on something I wish somebody had told me first. The network never sees the loss. Nothing in there reads that number. Not one weight in any layer is ever handed the score. What backpropagation carries is the slope of the score. How much the loss would change if the answer moved a little. So the question was never which rule gives the bigger number. It is which rule gives the bigger push. And to see that, we have to go one step further back to the thing we spent the whole of last episode on. The squash. A unit adds up its total, call that total z, and then squashes z into a probability between 0 and 1. Z is the part the network actually controls. So the only question that matters is how much the loss changes when z changes. For cross-entropy, the answer is so clean it looks like a typo. The push is p minus 1. The prediction minus the truth. The error itself, and nothing else whatsoever. The squash's own slope and the logarithm's slope cancel each other out, exactly. Those two functions were built for one another. For squared error, nothing cancels. The push is the error multiplied by the squash's own slope, which is p times 1 minus p. And p times 1 minus p is 0 at both ends. So here are the two pushes across the whole slide. This is the entire episode in one picture. Cross-entropy is a straight ramp. It is strongest exactly where the prediction is worst, and it only fades away as the answer becomes right. Squared error is a hill. It is strongest at a prediction of 1/3, where it reaches 0.296, and it falls to nothing in both directions. So at a prediction of 0.1, cross-entropy pushes with 0.9. Squared error pushes with 0.16, 5.5 times weaker. At 1 in 100, 0.99 against 0.02. 50 times weaker. At 1 in 1,000, a network as confidently, catastrophically wrong as it is possible to be, cross-entropy pushes with 0.999. Squared error pushes with 0.002. 500 times weaker. Read that curve again, because it is genuinely perverse. Under squared error, the surer the network is that it is wrong, the less it does about it. It goes quiet exactly where it needs to shout. That is an argument about a curve. Let us turn it into an experiment. The same 200 dots we have used since episode 2. The same network. 2 inputs, 8 units, 8 units, 1 answer, 105 numbers. The same starting weights. The same step size. The same 2,000 steps. One difference, and only one. This one is graded by cross-entropy. That one is graded by squared error. Cross-entropy reaches 95% at step 118, 99 at 225, every single dot by step 314. Squared error gets there too. 95 at 251, 99 at 496, every dot at 703. So squared error is not broken here. It is just slow. 2.25 times as many steps from an identical start, which is a real result and a slightly underwhelming one, and there is a reason for that. This network starts out unsure. At step 0, every prediction is hovering somewhere near a half, and near a half the two rules barely disagree. A half against a quarter. The push at step 0 is 0.33 for cross-entropy and 0.12 for squared error. 2.7 times, which is very nearly the speed difference we just measured. So the graph is right, but this experiment never went anywhere near the interesting part of it. Let us start it somewhere that does. Same network. I multiplied the starting weights by 6, which drives every unit deep into the flat part of its squash. Now it does not just start wrong. It starts wrong and certain. 48.5% of the dots correct, which is worse than a coin, and 89% confident about it. This is the corner of the graph that the gradient curve was warning us about. Run both. Cross-entropy is at 95% by step 54, 99 by 224. It finishes with every dot right. And squared error. It climbs to 89%, and it stops. For 1,000 steps, it never reaches 95. 22 of the 200 dots are wrong, and they stay wrong. Not because the network is incapable. It is the same network, and the other copy of it was at 95% in 54 steps. Look at its score, and then look at its push. Its score is 2.36 against cross-entropy's 0.0002. It is doing terribly, and the number says so. And the push it is getting is 0.0002. It knows it is wrong. It has no way to feel it. The scoring rule went numb precisely where the mistakes are. The network did not fail here. Its definition of wrong failed it. Now, that was classification, where the answer is yes or no. The other half of the job is predicting an actual number, and there the choice shows up somewhere you can see it with your eyes. 25 measurements. 24 of them are honest. One of them is a mistake. Fit a straight line through them by minimizing squared error, and this is what you get. Slope 2.1. Now delete the bad measurement and fit it again. Slope 1.77. 1 point in 25 move the entire line. Through the middle of the data, where every honest measurement lives, the fit is off by 1.23 because of a single number that was never real. Squaring is why. Under squared error, a point that is 10 away is 100 times worse than a point that is 1 away. So it will cheerfully wreck the fit for 24 measurements in order to get a little closer to 1. You can see it in the pull. That bad point is 28.9 away from the line, and it drags on it with a force of 57.8. So change one thing. Do not square the mistake. Just take how big it is. Absolute error. And now every point pulls with exactly the same force. 1, no matter how far away it is. Being 10 times further away does not make you 10 times louder. Same 25 points. Slope 1.77. Take the bad measurement out, and the line shifts by 0.11 through the middle of the data. Nearly 11 times steadier than squared error against the identical bad point. And you can have both. Huber loss squares the small mistakes and only takes the size of the big ones, so it stays smooth near zero and stops carrying past a threshold. Its line shifts by 0.06. None of those three lines is the correct one. They are three answers to a question the data cannot answer for you. And here is the version of that which is absolutely everywhere and almost never named. 100 measurements in 2 clumps, one near -1, one near +1, and about 2/3 of them are in the upper clump. Ask squared error for the single best number to predict, and there is an exact answer. It is the mean, plus 0.33. Now count how many of those 100 measurements are anywhere near plus 0.33. 0. Not one of them. Squared error's ideal answer is a value that never once occurred. Ask absolute error the same question and you get the median, plus 0.92, and 49 of the 100 sit within a fifth of it. This is not a toy. This is why an image model trained on squared error gives you a blur. Asked what a face looks like, it is being scored against every plausible face at once, and the thing that minimizes squared distance to all of them is their average, which is a smudge that is none of them. Squared error does not want to be right. It wants to be not too far from everything. Those are different jobs. So, what a loss function actually is. It is not the scoreboard. Nothing in the network ever reads the score. It is the slope. Every weight in every layer moves because of a derivative that started at the loss and was handed backwards, which makes it the one sentence in the entire system where a human says what they want. The layers, the widths, the activations from last episode, all of that is machinery for satisfying it. And that is why the obvious choice keeps being the wrong one. Squared error is what being wrong feels like to a person. Cross-entropy is what being wrong has to feel like to gradient descent. But there is still one number I have been quietly setting all series and never once justified. When the loss says go that way, how far do you actually go? Every run in this video moved in steps of 0.5. I chose that. At 10, the same network tears itself apart. At 1,000th, it would still be running now. Next time, the step size and why it decides everything. Learning rates, momentum, and the optimizer that almost every model you have ever heard of is trained with. The loss is the only place anyone ever tells a network what wrong means, so subscribe.